today's video, we're going to be looking at the standard normal distribution and look at some calculations on converting some scores into z-scores and looking at normal distributions in general. Here is a picture, a graph of the standard normal distribution. And if you'll remember, the standard normal distribution has the bell-shaped curve centered at 0, so the mean, median, mode would all be at 0. We have the inflection points being 1 unit away from the center. We would have the condition that the standard deviation, that the mean of this distribution is 0, and the standard deviation of this distribution is 1. If we go out 1 standard deviation on each side, we still would include 68%, 2 standard deviations, 95%, and if we go out 3 standard deviations, we would have 99.7%. Now, this distribution, having a mean at 0 and a standard deviation of 1, is pretty limited. However, we'll look at how we convert other scores into a standardized normal distribution as we move on. This should look familiar. This will be our conversion factor, and we'll talk more about this in a minute, but that's how we convert a distribution that's not centered at 0 and doesn't have a standard deviation necessarily of 1 to this type of a distribution. And again, we'll get back to that in a minute. All right, so let's look down at this example down below, and we have, this is number 20 in your book. We have Eleanor scored 680 on the math component of the SAT, and then she scored a 27 on the ACT. And we basically want to look at, we can't compare obviously these two raw scores to each other. This is much higher than this 27. However, we want to look at how would we compare relative to other people on SAT and relative to other people on the ACT. Which test did she actually do better compared to other students? So we need to know what is the mean and standard deviation of an SAT. And so we know that SAT scores are approximately normal, centered at 500 with a standard deviation of 100. So this would be from collecting a lot of data and finding the mean, the arithmetic mean, adding them up, dividing by how many there are, and this is what the standard deviation or the variability is, and the graph of the distribution would look like approximately a bell-shaped curve, so it's approximately normal. If we're not told that, then we can't assume that it's a normal distribution. We need to be told that something is approximately normal to be able to deal with some of the calculations we do further. But here's a picture of the distribution for SATs, centered at 500. Remember the inflection point located about here. This distance from the center needs to be 100. And so I labeled it, this is 600, here would be 700, and she got a score of 680. On the ACT, on the other hand, this distribution is also approximately normal. However, this, from the data that was collected at the time, the mean is centered at 18, and the standard deviation is 6. So I move over to this inflection point, I move 6 units over. And this would be 1 standard deviation away. Eleanor got 27 points. So if I just look at the location on each of the two graphs, her scores are different. They're not exactly the same, not terribly different, but they are different. And remember, we can find how many standard deviations away from the mean her score is, not just how far away she is, but how many standard deviations away she is, by converting her score to a z-score. And that's where we take the score that she got minus the mean of the distribution, dividing it by the standard deviation. And this gives us a z-score, we call it, and that tells us for this calculation that her score is 1.8 standard deviations higher than the mean for the SAT score. Done the same calculation for the ACT. Take her score minus the mean, divide it by a standard deviation, and we find out that her ACT score is 1.5 standard deviations higher than the mean. So relatively on these two tests, her score is higher, more standard deviations away from the mean on the SAT than it was on the ACT. So we would say she did better compared to other students on the SAT. Now, we want to remember that sometimes we have to work with some numbers that aren't contained in that one standard deviation away being 68%, two standard deviations away being 95%, and so on. And sometimes we have z-scores, and I have some examples here, where we have to look up in a table to determine some probabilities. So let's say we have this standard normal distribution. And the first question asks, what is the likelihood of randomly picking a number and getting a score that is less than 2.85? So we would want to look at, we can see that 2.85 is way up here on this standard normal distribution. And so what's the likelihood of getting something less than 2.85? Well, there are lots of scores that are less than 2.85. And remember, the way we find that probability is we have to look on a table that's located in the front cover of your book. Also, there's one in the back of the book, and I have an example of a table here. And so we want to look up, here's our standard normal distribution, and here's a z-score located at 2.85, and we want to find all of this area below. Remember, the area underneath the whole density curve is 1, and we want to find what the area is that's less than the 2.85 value. So I turn my table, and remember we have a negative page. We won't be using that one right now. And we turn to the positive page. And so I look down my column and find 2.8. I work across the top and I look for 0.05. And I come down and we'll go across and I have 0.99878. And that's the area under the density curve. It's also the likelihood that if you took a standard normal distribution and randomly picked a number, the likelihood that the number would be less than 2.85. Now, we know that the area under a density curve is 1. So if the area below 2.85 is 0.9978, then the area that is above 2.85 is going to be its complement, or 1 minus this value. So we have the 0.0022. Now, we could also use some symmetry of the curve. The standard normal distribution is symmetrical. And so if I am looking for, here's a 2.85 score, and if here's negative 2.85, and if I want the area above a z-value of 2.85, I can actually look up the area that is less than, got a little lead problem here, is less than negative 2.85. And remember, we have a negative page on our chart. So I could look up negative 2.805, and I could find this value of 0.0022 by using the negative page. So drawing a picture is really important to see if your answer makes sense. Now I want to find the likelihood if you randomly pick a number from the standard normal distribution, and remember that's centered at 0 with a standard deviation of 1, what's the likelihood that your score would be higher than negative 1.66? And when I draw the picture locating negative 1.66 and shading above, I know it's way bigger than 50%. Now remember, I have a choice on how I'm going to determine this answer, which is the correct answer. I can either use my table, but my table always tells me the area below a number. And so if I look up the z-value of negative 1.6 and go to the 0.06 column, and I find that the answer here is 0.0485, that's this area down here. So I would have to take 1 minus 0.0485 to obtain this. I can also use the symmetry of the distribution. And if I know that here is a value of negative 1.66, and here's a value of positive 1.66, and if I want the area above negative 1.66, that really will be the same as finding all of this area that is below positive 1.66. So I could look up on the positive page the area below 1.66. And the nice thing about that is it avoids me having to do a subtraction. Then remember what we do if we want to find the area between two numbers. And the context of this would be, again, if you have some distribution that is centered at 0, it's normal, bell-shaped, and it has a standard deviation of 1, what's the likelihood that if you kept picking scores over and over and over from that distribution, what's the likelihood that your scores would be something between negative 1.66 and 2.85? You can see it's a fairly big answer if we draw a picture and shade that in. But remember, we find the area below the larger of the z-scores, and then I find the area below the other z-score, the smaller z-score. This area is too big, and it includes this little tail that I don't want to include, so I want to subtract that little area away, and that will give me the area between those two z-scores, which is also the likelihood that if you continue to pick numbers over and over from the standard normal distribution, the likelihood that your score will be between those numbers. Okay, now let's turn the page. Now an application question. So the scores on a specific intelligence test for this age group is approximately normal and is centered at 110 with a standard deviation of 25. Draw my bell-shaped curve, note where the inflection point is, drop straight down, and I should go 25 units this way of the mean to get to this score, and so on. So I can label this axis. Now, I want to know what percent of the people have IQ scores who are in this age group that's higher than 100. So this would be the notation that I would use. I want to find the probability that I get a score. And notice I don't call it a z-score here. It's an x-score. A z-score is specifically for a standard normal distribution that's centered at 0. So I want to know what's the likelihood or the probability of choosing a score and it's bigger than 100. Now, bigger than 100, if it were at one of these specific integer number of standard deviations away, then I could use that 60, 68, 95, 99.7 rule. But 100 is maybe about here. And so I don't know exactly what that area is above that because it's not at one of those specific numerically integer values away. But what we want to do is we want to find converting that to a z-score, finding how many standard deviations below the mean my score is. So now we're converting it to a z. I take my score minus the mean divided by the standard deviation. I find out that my score is 0.4 standard deviations below the mean. That's why it's negative. And then I can utilize the same ideas that I did on the previous page. I want to find the area in this case. I want to find the area above that number. So I can either look up negative 0.4, and be careful, it's not this negative 0.4, and look up this value here, which that will not be the answer because that's the lower tail, that's the area below the z-score, and take 1 minus that. Or I can look up the area that is below positive 0.4 and utilize the symmetry of the distribution to get this answer directly. Here's a second example. What's the likelihood that you randomly pick a person from this distribution and get a score that is higher than 150? Once again, 150 is located somewhere between two integer number of standard deviations away from the mean. And so if I take 150 minus the mean divided by the standard deviation, I find out that I'm actually 1.6 standard deviations higher than the mean. So in this picture here, I would be about at this point. 1.6 standard deviations. Now I look at the sign. I do want it to be higher, so I am looking for this area above, and I can see it's not going to be very big. So I can either look up the z-value of 1.6, knowing that that's going to give me the area below the value, and then do a 1 minus that value to find this answer, or I can look up negative 1.6, and instead of really finding the upper tail that I really want, I could find the symmetric lower tail to get this value. Now we do need to be able to work backwards as well, and you did have some practice with this in FS, and we'll go through one example, and then you'll get to practice on your own. So we have how high an IQ score is needed to be in the highest 25%. So if you know you scored at the highest 25%, what would be the lowest score necessary to be in that upper 25%? So I drew my little bell-shaped curve, and I know that my value is higher than the mean, because if this answer had said 50%, then we would know that it's right at the mean score. But we know that we're above the mean, and we know we want this area to be 0.25. Now this is not a z-score, that's the area. So we know the area that corresponds with this, and we really want to know what is the z-score that corresponds with an area above it being 0.25 and the area below it being 0.75. So I took my table and I looked up within these 4-digit numbers. I need to find an area of 0.75. And it's not an exact value that's on here. And I can see I have a 0.7486 and a 0.7517. And I've kind of written that down in here. And on my z-table, I can see that the 0.7486 has a z-score of 0.67, and that's 14/10,000ths too small of an area. And the other is at 0.68, has an area below it of 0.7517. And that area is 17/10,000ths too big. So if I were going to pick one that's closest, I would use the 0.67, but I actually split the difference and went halfway between 0.67 and 0.68, and I'm calling the z-score 0.675. And then we'll go back and look at doing a conversion. So here's our formula for the z-score, and we know that the z-score that we're looking at is 0.675. We don't know this score, but we know when we subtract the mean from it and divide it by the standard deviation that we're going to get this 0.675. Do a little bit of algebra, multiply both sides by 25, and then add 110, and we get this value. So we know that if someone had a score of basically about 127, they would be in the 25th percentile. Now we'll finish up looking at the last page. And how do we tell if some distribution is approximately normal? If I give you some data, like here's an example, it says let's start by examining some data on unemployment rates in the 50 states in November of 2009. And these are kind of light to see, but we have a little graph, a little histogram graphed. And if we look at that graph of the 50 states, we can see a little indication that the graph looks quite close to being a bell-shaped curve. It's not perfect by any means. So that's the first point, is if you have a set of data, plot the data. You can make a dot plot, a stem plot, a histogram to see if it looks like it's approximately symmetrical and if it's bell-shaped. Now, we know another characteristic that the data should have if it's normal is if we take the mean, find the mean of the data, and find the standard deviation of the data by our mean, add them all up, divide by how many there are, and the standard deviation, take each number minus the mean squared, divide it by n minus 1, and then square root it to find the standard deviation. So if I take the mean and add on one standard deviation, and take the mean and subtract away one standard deviation, and that comes out to be about a roughly 6.5 to 10.9, and count how many of these are within that region. And we find out that 72% of the scores are within one standard deviation of the mean. Likewise, find the mean plus or minus 2 standard deviations, and we find that 48 out of the 50 states are within 2 standard deviations, and the mean plus or minus 3 standard deviations, that all of them. Now, Naturally, we'd love this number to be exactly 68, and this number to be exactly 95, and this to be exactly 99.7. But our graph of the 50 data points seems to be pretty bell-shaped, pretty symmetrical. It seems to follow this 68, 95, 99.7 rule fairly well. So our indication with these two would be, looks like, it's pretty close to a normal distribution. Not perfect, but we don't expect perfection when we have just a sample of 50 scores. Now, a third is to make a normal probability plot, or it's also called a normal quantile plot. And this is a plot that we actually will not calculate out longhand. And we have a little blurb here that talks about what's happening. That you, and again, we are not going to practice doing this longhand. This is a type of thing that it's kind of tedious and repetitive. We basically want to know what should we see in a plot so that we can determine from this normal probability plot or normal quantile plot whether we have a normal distribution or not. And so basically what is happening is you're plotting each of the observations against its corresponding z-score. And you can read through this to hear the details of what happens in order to do the calculations on it. But in the end, we would have the score versus its z-score. And what we want to see is if we have approximately normal data, which this is the data from up above, notice that this is very linear in nature. And so if you plot a normal probability plot and your data looks to be quite linear in fashion, then your data is approximately normal. If you graph one of these plots, and this will be the sixth plot in your chart, I'm not going to practice one with you. You can do this in class. But when you go to stat plot, it's you have scatter plots and so on. The sixth plot is your normal probability plot or your normal quantile plot. And if you enter all of the data from up above, these 50 unemployment rates, into list 1, and then go to stat plot and turn on the sixth plot and graph that, and you can just use the zoom stat, you will find this is what your calculator will graph, and it will graph approximately a straight line, or the data will approximately form a straight line. And that is going to predict that your data is approximately normal. Now it's time for you to practice some on your own.